define for velocity as the velocity through space-time. Now we're in the position to start to examine momentum and energy because we have a nice definition of velocity, and we require that to define momentum in space-time. So we're going to start with form momentum, and we can define the relativistic momentum just analogously as we do to 3 momentum, or momentum as you're familiar with, just mass times velocity. Here we just define the form momentum as mass times the 4 velocity. So P mu is equal to mv mu, where now v mu, remember, is the 4 velocity. That's just a natural way to define it, and we'll see this will be very useful in what we do, and it will lead us to the definition of energy as well. So what do we expect for this particular quantity of form momentum? Well, we expect 3 things. 1, we still expect to have conservation of 3 momentum. Under relativistic scenarios, we still expect to have 3 momentum to be conserved. That has not changed because that is still observed in relativistic collisions. Second, conservation of energy should be conserved as well relativistically, and we will impose these two and make sure that this definition adheres to that. The third condition is the correspondence principle, which we've done before, is that the low velocity limit should correspond to classical values. That's just saying that if the way we define this, if we take v going to 0, we expect to get what we're familiar with in classical physics. That makes sense, because it should tie in with our classical ideas. So first, let's examine the 3 momentum, the classical momentum that you're familiar with from the first quarter of this course. So classically, we have px is equal to mvx, the velocity in the x direction, which is just mass times delta x over delta t. Now relativistically, we have that px, denoting it this way, is equal to mvx, the x component of the 4 velocity, that's different now, and that's equal to m delta x over delta tau, the proper time. Okay, so that's the difference now that we have. Well, remember that delta t is equal to gamma delta tau, so we can rewrite this as gamma m delta x over delta t. Just in one particular reference frame, we just use gamma to relate it, and we see that says gamma m vx, the x component of the 3 velocity, well, that's equal to gamma px, our classical 3 momentum. Well, we see right away that this satisfies the third requirement because as the velocity goes to 0, gamma goes to 1, and our x component of the 4 momentum goes to the x component of the 3 momentum. So that satisfies the third requirement for the spatial component of the 4 momentum. Now, we want to talk about conservation of momentum for old non-relativistic observers. Let's consider a particular case. We have some frame S where a particle travels within this reference frame with some components of 3 velocity vx, vy, and vz. So this is the 3 velocity we're talking about because we have the lower indices. And it's moving with respect to the origin. Now consider another frame S prime which is moving with respect to frame S in the x direction with velocity u. Then we have that vx prime is equal to vx minus u, vy prime is equal to vy, and vz prime is equal to vz. This is just the Gaussian transformation for these velocities. And the 3 momentum will transform as follows. Px prime is equal to px minus mu, py prime is equal to py, and so on. Well, what we have here is what we knew before, is that if the momentum is conserved in frame S, it will be conserved in S prime classically, because m and u are the same before and after the collision. The reference frames continue to move at the same speed with respect to each other. But let's examine this 3 momentum under a Lorentz transformation, because that's the proper way to do it in terms of relativity. So if we're dealing with higher speeds, say u is not small compared to the speed of light. Well, under the Lorentz transformation, we have x prime is equal to gamma x minus vt, and the same for t prime. This goes back several lectures. This is the relation between the 2 reference frames. The addition of velocity formulas gives us the following. These 3 components, vx prime, vy prime, z prime, and this is for the 3 velocity. Now, note here, vy prime and vz prime, if you look at those expressions, they depend on vx. So there is a kind of a mixture between the different directions, and normally those are taken to be independent directions. What we see from that particular mixture is that classical momentum is not conserved under Lorentz transformation. You get all this mixture of the 3 different velocities. So let's examine conservation momentum for the relativistic definition of momentum. And that's here, p mu is equal to m delta s mu over delta tau. Remember, delta s mu is just the interval. And again, we'll consider frame S and S prime with respect to each other with velocity u. So we'll have the following forms for the 4 momentum. Px is equal to mvx, py is mvy, so on. Pct is equal to mvct. Those are the components of the forward momentum in terms of mass times the forward velocity. And now if we change reference frames, the difference here now under Lorentz transformation, delta tau is the same in all reference frames. So the Vx component, for example, is delta x over delta tau. Delta tau is the same in all inertial reference frames, but delta x will change. Because of that, we get the following forms. We just take delta x is equal to gamma delta x minus p delta t, and we get the following form. Px prime now goes to gamma times px minus u pct, the time component of the forward momentum. Py and pz transform just into themselves because delta y is equal to delta y prime because the movement is only along the x direction. And the time component will change as follows. It's easy to show. So again, this is just a Lorentz transformation between the px and the p prime, the s frame and the s prime frame. And we see now that since gamma and u are the same before and after collision, we consider a particular collision, say, between two particles, the momentum will be conserved in both s and s prime. Because if it's conserved in s, it will be conserved in s prime, because of that invariance of u and gamma before and after the collision. So this tells us that momentum is conserved for this relativistic scenario under the Lorentz transformation, and this is a valid definition. And again, when we go to the low velocity limit, we get the 3 momentum back, which is good. So this is a nice definition of momentum, and we're going to go in the next lecture and discuss the last component, the PCT component, and see what that is, because that has no classical analog if you think about it. What we've been doing is arguing here between the 3 momentum and the spatial components of the 4 momentum, but we haven't discussed this last component because it's a little strange. We'll do that in the next lecture.